Hey there, y'all. Today we're going to look at 1.3 on the laws of exponents. In this section, you're going to be able to simplify exponential expressions using the properties of exponents. And this falls under the standard of FIF 8b, where we're going to interpret expressions for exponential functions by using the properties of exponents. So first we've got to look at what are the properties of exponents. And these properties should not be new properties. These are properties that you should have seen in middle school to work with exponentials. But we are going to look at one or two new ones that maybe you've not quite seen before. And so here we go through these. So the first one is the product of powers. And we've actually used this a little bit in section 1 and 2 of this unit, where if we have a base that is the same and we're multiplying them together, we will add the powers. And that's what we see with the property. A to the m times a to the n is equal to a to the m plus n. So an example of this would be like 4 to the second times 4 to the fifth. Our bases are the same, so that will stay 4. And then we will add the exponents, 2 plus 5, giving us 7. Or we could do it with variables. X to the fifth times x to the eighth. Again, the bases are the same, so we'll keep the base. And we'll add the exponents. 5 plus 8 is 13. Okay? The power of a power property is where we have one base raised to a power, and then that whole thing is raised to a second power. When we have that happen, we will multiply the powers together. And so, for example, if I have 7 squared, then raised to the third power, the 7 is still my base, and we're going to multiply the 2 and the 3 to give us 6. We could also do that with variables, y to the fourth raised to the third. So again, one base with 2 connecting powers. We're going to multiply those powers, 4 times 3, giving us 12. And so y to the 12th. The third property that we have is the power of a product property. And so this is where we have two bases. We have a times b being raised to a single power. And so we have to think of it kind of like the distributive property, that this power is going to distribute to both the a and the b, and we get a to the m times b to the m. And so we might see it like this. 2 times 3 to the fourth would mean that fourth power is going to go to both the 2 and the 3. And so we get 2 to the fourth times 3 to the fourth. Again, we might see it with variables as well, or we might even see it with a number, with a coefficient. So we could say like 5x to the third power. The power would go to both the 5 and the x. This is the case where we see those parentheses, so that power is going to go to both. Remember, when there's no parentheses, the power only goes to what it's directly attached to. And so the 3 comes to the 5, so 5 cubed, and the 3 to the x cubed. And so those are our product rules. And so now we're going to look at a couple of quotient rules, which are similar, but again, we're going to need to deal with the different operation. And so the first one we have is the quotient of powers. Similar to the product of powers, with product, we took the two powers and we added them together. But with quotient, we're dividing, so we're going to subtract the two powers. And so here we see a to the m over a to the n, and that's going to be a to the m minus n power. And so an example of that, we would have like 5 to the 6 divided by 5 to the fourth. The 5 is still the base, and we're going to subtract the powers. 6 minus 4, giving us 2. Again, we can also see that with variables. X to the 8th divided by x to the 5th. 8 minus 5 will give us x cubed. Our next power property is the power of a quotient. Again, similar to power of a product, we're going to take that power and distribute it to both pieces. The power will go to the a and to the b. It'll go to both the numerator and the denominator. And so we might have 4/5 to the second power. And so this square will go to both the numerator and denominator, so we get 4 squared over 5 squared. Now you see I'm not simplifying any of these numbers. I'm not finding what like 4 squared or 5 squared is. That's something that if we needed that number we could do later on. Right now we're just focusing on being able to use these power properties. Okay. Another example with variables, we might see like x to the or x over y to the third power. And again, the power would go to both. So x cubed over y cubed. Okay. The last two properties deal with how we think about positive and negative exponents. And I actually want to show you an example on this. And so we might talk about like 3 to the first power, and 3 to the second power, and 3 to the third power. And we can find all these numbers, right? So 3 to the first, well, that's just a singular 3. So 3 to the first is just 3. Because remember, anything to the first power is what? Itself, right? 3 squared, that's 3 times 3, so that's 9. And then 3 cubed, so that's 3 times 3, that's 9, times a third 3, so that's 27. And then 3 to the fourth, so that's 3 times 3 is 9, times 3 again is 27, times 3 again is 81. And so 3 to the fourth is 81. And so if you look at our pattern going up the chart, we're multiplying each time by 3. Well, we could also look at this going the other direction if we're reducing the powers, because we want to be able to get to 3 to the 0, and 3 to the negative first, and 3 to the negative second, and so on, and see what happens. And so 3 to the 0, well, we're going to have to backtrack. So instead of raising our power and multiplying by 3, we're working the opposite direction. So instead of multiplying by 3, we would be dividing by 3. So we would divide by 3, divide by 3, divide by 3, and eventually we get down here to now we're here coming down from the first power to the 0 power. So what are we going to get when we take 3 and divide it by 3? We get 1. And so 3 to the 0 is 1. And 3 to the negative first, we continue the pattern. Again, we're dividing by 3. So we're not going to get a negative number. That's a misconception here. A lot of people want to say that a negative exponent makes a negative. That's not true. A negative exponent is going to make something deal with fractions. And so 1 divided by 3 is 1/3. And if we go to 3 to the negative second, we're dividing by 3. But remember, if we're dividing and we're dealing with fractions, we're really multiplying by the reciprocal, right? So we'd be doing 1/3 times 1/3, which gives us 1/9. And so we see we're getting smaller and smaller fractions. I can go to 3 to the negative third. It would be 1/27. And so we see that pattern starts here. We see 3 and 3. And we see 9 and 9. And so we see the relationship. And so coming back to our properties, we see that the 0 power, a to the 0, anything to the 0 is equal to what? 1. There is one exception to that rule. A cannot be 0 because, again, we would be dividing by 0 in that case, and so it doesn't work. Also with negative exponents, a to the negative n, again, it becomes a fraction. So we'll take that whole power, the base and the exponent, and we will shift it from the numerator to the denominator, and the power will change its sign. And so we would see something like this. We would see 4 to the negative third is equal to 1/4 to the positive third. Or if that negative exponent is already in the denominator, like 1/x to the negative fifth, well, the same rule applies. Well, if it's already in the denominator, to switch its position, it's going to move it into the numerator. And so 1/x to the negative fifth will just be x to the positive fifth power. Okay? So those are our power properties that we're going to look at. We're going to look at some examples doing all of these, and so that's what we're going to look at next. So in example 1, we're going to look at our product rules. And so we have some different examples here using those properties. And in example 1a, we've got 3 squared times 3 to the 7th. And so which property we're going to use here? Well, we've got two separate bases that are the same being multiplied together with exponents attached. And so this is our product of powers rule. And so our base will stay the same. And so we will take the powers, the 2 and the 7, and we're going to do what with those? We're going to add them. And so 2 plus 7 gives us 9. And that's it. Now again, if we needed the number, we can multiply it out. We can go to our calculator and get what 3 to the 9th is. But for the purposes of working with these power rules, we just want to leave this as our final answer. So we're not going to change anything. Okay? In example B, we see some variables involved here. X squared times x to the 6th times x. So we're actually multiplying 3 things together. They're all the same base, so we're using the same property. And so we're going to add all the powers together. And so we got 2 and 6. And don't forget that this x here has a power of 1. So 2 plus 6 plus 1 is 9. And so we get x to the 9th. And again, there's nothing else we can do, so that's the final answer there. Okay? In example C, we see that we have a singular base here raised to a power, and then that's raised to another power. And so that's our power of power rules. And so we're going to take these two exponents and we're going to multiply them together. And so our base stays the same, and 2 times 7 is 14. And again, there's nothing else that we're going to do there. Again, if we needed the number 4 to the 14th is going to be a very large number, we would get that number. But 4 to the 14th is perfectly fine to leave as is. All right. In example D, we see a variable here in cubed being raised to the 6th power. So again, this is power of powers. And so we're going to multiply these two powers together. So n to the 18th. In example E, we see 24 times 13 raised to the 8th power. Now, using order of operations, can I multiply 24 times 13 and get what it's going to be and then raise that number to the 8th power? Sure. But is that always helpful to our situation? 24 times 13, that's going to be a decently large number. And if you've got your multiplication chart, you would have 24 times 13 on that chart. But using the power rule here, we can actually distribute this power of 8 to both, and we get 24 to the 8th times 13 to the 8th. Now, 24 to the 8th is a huge number. 13 to the 8th is a huge number. And so multiplying those together, again, we're going to get a very large number. But the point of the property is that we're able to separate this out into its separate pieces. And down the road, we might need those separate pieces as we work through a problem. Okay? In example F, we see one with variables. And so, again, this power distributes to both. And so negative 4, we're going to put that in parentheses because we need to keep that negative with the 4 squared. And then we're also going to get z squared. Now, this is what I'm going to actually simplify because I want to talk about this property a little bit further. Negative 4 squared, that means I'm doing negative 4 times negative 4. Well, a negative times a negative is a positive, and so it's going to give us positive. And then 4 times 4 is 16, and so this is 16z squared. And so, again, one like this, while we're working with these properties, it's fine to leave with the squares or whatever the power might be on it, especially if it's a larger power. But later on, as we talk about quadratics, we're going to need to be able to distribute this power and simplify it. And so we're going to want to be able to multiply that power out and get like negative 4 squared becoming positive 16. All right, let's look at G. This one's a little bit more involved. This kind of combines all of our properties together in this. And so let's see what happens. And so we've got 2x cubed squared times x to the 4th. Now, order of operations still has to apply. And so things in parentheses have to go first. Well, there's nothing I can do inside of here to simplify it. But then I've got this power here. And so this is a power outside of a product. So that's going to distribute to both the 2 and to the x cubed. And so I'm going to get 2 squared times x cubed squared. And out back here, we've still got our x to the 4th. We'll pick that up in a minute. And so simplifying this, 2 squared is 4. X cubed squared, we do need to do that power rule. So that's going to be multiplying this power, giving us x to the 6th. And then I've got x to the 4th still sitting back here waiting patiently. Now I can combine those two x's together. And so we're going to add those powers. And so our final answer here is 4x x to the 10th. So again, using those power rules to combine them together into one simplified answer. Okay, so that's it on our product rules. We're going to get into the quotient rules next and look at a few examples of those. So let's go down to those. So as we look at example 2, we've got a few problems here we're going to look at to be able to simplify quotient rules. And so remember our quotient rules that we looked at the top of the lesson. And so in example A here, 6 to the 11th over 6 to the 5th. And so again, we're going to subtract the powers here. So this is going to give us 6. 11 minus 5 will give us 6. And again, simplifying here, we're going to leave it 6 to the 6th. We're not going to worry about multiplying all the way out and getting what the simplified value would be. Okay, so this would be our final answer here. Now, one thing, let's just talk about it. This is a secondary example here. What if I had it the other way? 6 to the 5th over 6 to the 11th. Well, we're always going to subtract numerator minus denominator. And so subtracting those powers, we would get 6, 5 minus 11 would be negative 6. Now, we're going to get into example 3 in a moment and talk about those negative exponents, but we don't want to leave a final answer with a negative exponent. And so we would actually rewrite this as a fraction. And so because I have the negative exponent, it's going to switch its position in the fraction, and so it's going to be 1 over 6 to the 6th. And again, we're not going to simplify that number at this point. We're going to leave it 6 to the 6th and leave it as that fraction. Okay. So now let's look at example B. Here we've got 1 over y to the 5th times y to the 8th. Well, let's rewrite these as fractions so we can multiply them together first. And so remember, to multiply fractions, we multiply straight across, numerator to numerator, denominator to denominator. And so 1 times y to the 8th, that's y to the 8th. And y to the 5th over 1, so that's y to the 5th. And so now I've got it as a fraction, so we can use our quotient rule. And so we'll subtract these powers, 8 minus 5, giving us y to the 3rd. Okay, so again, if we've got fractions being multiplied together, get it together into one fraction, and then we'll simplify from there. In example C, we see our power of a quotient rule. And so this cube is going to distribute to both. And so we'll end up with x cubed over y cubed. So again, the power just goes to both. And again, if we could simplify certain things, we would. But again, there's nothing to do here, so we leave it as is. In example D, again, we see another power here being applied to a quotient. And when we see this negative sitting out front, we can attach it to either the numerator or the denominator, not both. And so I'm going to attach it up here to the 7. And so when I rewrite this, it's going to be negative 7 squared over x squared. Because again, we want the power to go to both the numerator and the denominator. And so negative 7 squared, just simplifying this a little bit, we get 49 over x squared. So again, simple ones we can simplify if we need to, but the point here is understanding how that property works. Okay, so let's go ahead and look at example E. This one, again, combining a little bit more together in our rules. So let's see what happens here. Well, we've got 2s over 3t, all raised to the 3rd power, and then we've got t to the 5th over 16 being multiplied to that. So we've got to deal with this power first. It's got to come to all of this. And by all of this, it means we're actually using two properties here. And we can write it in 2 steps. So 2s to the 3rd over 3t to the 3rd. And then on the back side, we've still got our t to the 5th over 16. But now I've got this power to a product here and this power to a product here. So we've got to multiply that out. Or not multiply, but we've got to distribute that power out. And so we're going to get 2 to the 3rd and s to the 3rd over 3 to the 3rd and t to the 3rd times t to the 5th over 16. So we're getting there. We're going to simplify these in this case. And so our next line, we're going to get 8s cubed over 27t cubed times t to the 5th over 16. Now, we're going to multiply this together and get it into one fraction. And so doing that, we're going to get 8s cubed t to the 5th over 27 times 16. So we could do that multiplication, but actually I'm going to show you a little way we can reduce this pretty quickly here with the numerator. And so we see the 8 and then 27 times 16. This is a multiplication, not a decimal. T to the third. And so we see here in this piece, we have some t's that will simplify. And so coming out, t to the 5th and t to the 3rd, that's going to subtract. And so that's going to be t squared. The s has nobody to work with, so that's going to stay in the numerator as well. Then we look here at the 8 and the 16. 8 over 16 is a half. So this can reduce to 1. This can reduce to 2. And so now I've got 27 times 2. Well, that's a lot easier. That's just 54. And so our final answer is s cubed t squared all over 54. Okay. So again, we want to be able to see through this whole property to be able to reduce it. All right. So let's go to example 3 and 0 and negative exponents. And so remember, anything to the 0 power is what? 1. So when we look at 2/3 to the 0, well, anything that's in that parenthesis that's being raised to the 0 power will just be 1. The answer is 1. Okay. Now, if I had other things outside, like if this 2/3 to the 0 is being multiplied by 5 or added by 7, those things would still get involved, and I would be able to multiply by that or add or whatever operation's going on, and my final answer wouldn't be 1, but the part that was to the 0 power became 1. Let's look at example B. We've got negative 8 to the negative 2nd power. Again, misconception here, the powers are not going to cancel, right? We're not taking negative times a negative, okay? Remember, this negative power is going to make it a fraction. And so our next step here is to rewrite it as 1 over negative 8. The power becomes positive now because we moved it from numerator to denominator. And now we can take this power if we need to. And so negative 8 times negative 8 is positive 64. So this is 1 over 64. Example C, 1 over 2 to the negative 3rd. So again, we see a negative exponent. That's going to make us switch its position in a fraction. So if it's already in the denominator, it's going to move it to the numerator. So that's going to bring this up here. And so we're going to get 2, and that's going to be to the 3rd power. And 2 to the 3rd, if we need it simplified, would be 8. So again, we see how that negative exponent makes it switch its position in a fraction every time. If it was in the numerator, we're going to the denominator. If it was a negative exponent in the denominator, we're going to that numerator. So that's where we're at there. And so the last couple of examples we're going to look at real quick are just combining some different properties that we've got. And so let's look at those. So we're looking at example 4a. 5 to the negative 3rd to the negative 2nd. So there's two ways to attack this problem. Because it's power to power, I'm going to attack it that way. You could deal with the negative exponent and move it, and then there's another negative exponent, so you're going to have to move it again. But watch what happens with these two powers when I multiply them together. Well, the base is still 5, and I'm multiplying these two numbers, negative 3 times negative 2. Well, negative times negative is positive, and 3 times 2 is 6. And so I get 5 to the 6th. Again, if I need the number, we can expand it out. But we're going to leave it 5 to the 6th in this case. And the rule of thumb here is if it's a really simple number like 4 squared giving you 16, do it. Right into 16. But if it's going to be like 5 to the 6th, and 5 to the 6th is 3,125, we don't need to necessarily expand it out every time. It might be easier to leave it as a exponential number. In example B, we've got 3x y to the negative 3rd, 9x cubed, and this is a typo, but the y should be a base. So I'm going to fix that typo real quick. There you go, like magic, it's been fixed. So let's look at what happens here. And so like we did with our radicals, we want to kind of look at this in pieces. So when we look at the 3 and the 9, that's just a fraction that's going to reduce. So 3 over 9, well, 3 goes into 9 3 times, so 1 and 3, dividing them both by 3, right? So we're going to get 1/3. We go to the x's. We've got an x and an x cubed. This is quotient rule, so we're subtracting. And so 1, sorry about it jumping, minus 3 would give us x to the negative second. We'll fix the negative exponent on the next step. And then the last one, we've got y to the negative third and a y. Again, there's a 1 on this, right? And so simplifying that part, negative 3 minus 1, well, negative 3 minus 1 is going to give us negative 4. And so now I've got two negative exponents here. Those will go from the numerator down to the denominator. And so our final answer, the 1 is the only thing left in the numerator. And again, if everything moves out of the numerator, we have to have something there. 1 is the default. Okay? And so everything else moving to the denominator, the 3 is still there. This will become x to the positive second and y to the positive fourth. This would be our final answer. Okay? So as we look at all these examples here, we're using all the properties to be able to simplify these exponent rules. And we're going to use these as we go through exponential problems and as we go through power rules further through this semester. So if you got any questions, make sure you leave them in the video check, and then I'll catch y'all next time. Y'all have a good one.